All right, so we're talking about interfaces and stacks. So we've seen two implementations of a stack. I'm going to show you the third one quickly this afternoon. And before we do that, since we have multiple implementations already, we might as well make an interface for our stack class, so for stacks. So to make an interface, it's very straightforward, right? You just declare an interface called stack, and then you put in the methods that you want every stack to have. Stacks only have two methods. Plus, we're going to add size and isEmpty. I'll talk about isEmpty in just a second. So add two more methods to our stack interface. Otherwise, it's just push and pop. Right? Now remember, in an interface is a specification, right? So you do say, what is a stack for, right? And what all the methods do, right? But typically, you have no implementation of any of your methods, right? So every stack has a push method that takes in a string as an element. Every method has a pop method that returns a string and removes the top element of the stack. Now notice here we have isEmpty. So we also have a method size. So every stack has a size method. IsEmpty is marked as a default method. So default methods in an interface are methods that are allowed to have an implementation. When you implement the method, though, you can only implement it in terms of the other methods in the interface. So isEmpty you can implement using size, right? You just check is the size 0 or not. Right? So we can actually provide an implementation of this method if we want to. We don't have to. We could just leave it as a plain old interface method and then force everybody else who implements the interface to also provide the method. But because we can implement the method, it makes sense to do so here. Right? The restriction, again, is that you must use methods that are in the interface. You're allowed to use methods. So if this interface implements another interface or extends another interface, then you could also use the methods in the other interface that you extend. Finally, you're allowed to use methods that are in object because any class that implements stack is also a big O object. So you're allowed to use methods like toString and equals and hashcode in a default method if you want. Right. So default methods are actually new-ish in Java. They were added in version 8, I think, of the language. Did I tell you where? Yeah, they were added in version 8. Right. So an interface is allowed to have a default method, but a class cannot. Right? Classes provide method implementations, so there are no default methods in classes. So yeah, I mentioned this. So default methods have an implementation. You have to implement the method in terms of the interface itself, or in terms of the method in object, or in terms of any of the super interfaces of the interface. We'll talk more about super interfaces and inheritance probably in the next lecture. Right. So for example, if you remember that list is actually, so the list interface is actually a sub-interface of collection. So if you had a default method in list, you could actually use one of the methods in collection as well. I mentioned default methods are new-ish in Java. So they came in version 8 of the language. And the reason they were introduced is because there was a big change in version 8 of the language. And so the change was big enough, so it was a very significant feature actually, that was added to the language. And when they added this feature to the language designers realized that many of the existing interfaces had to change. And there's a problem with interfaces. So if you release an interface and it becomes widely used, you really can't change that interface anymore. Because if you make a change to the interface, everybody who used your interface now has to re-implement all their classes to add or remove whatever methods you added or removed to the interface. This is exactly the problem that the language designers were in. They have a standard, very large, very heavily used standard library, has many interfaces in it. Now they have to make a change to it. So they had a few options here. One of them was to add default methods. And so that was the option that they chose. So they decided it was better to add default methods to the language rather than force everybody to re-implement all their classes that used an existing interface. Not everybody was happy with that decision, but that's the decision that was made. Right? So that now we have default methods in interfaces. All All right, so we have two existing stack classes. We can easily change them so that they now implement the stack interface. Oh wait, I guess we can't. So we're going to do this for a stack of string. Our array-based implementation is a stack of int, so we can't actually make that stack implement this interface. But we're going to fix that shortly. So I'm going to show you how to create generic classes in a few lectures from now. Okay, so our list-based stack, if we want it to say that it implements the stack interface, it's easy. You just change the name of the class, right? Because it used to be stack. So I have to change it to something else. And you say that it implements the stack interface now. That's it. You're done. So if you want to implement an interface, it's normally pretty easy to do. All right, so keep that in mind. So we now have a stack interface. We're going to come back to this to the stack interface in a later lecture. Well, I guess we'll do it here. But you're going to see it in a lot more detail in a later lecture. OK, so the third way to implement a stack you guys are familiar with, I'm pretty sure. You know that you can use some sort of linked list-like structure. Right? There is a reason why you'd want to do this. So for any list or array-based stack, pop is always in O1. But push occasionally is in ON. So when the stack size is equal to the capacity of the underlying array, either in your array list or in an array-based stack, right, you have to resize the array, and that always takes time proportional to n. Right? So push is in worst case big O(n), which may not be acceptable depending on the application that you're trying to write. Right? So in other words, someone may need a very high performance stack where the time required to push and pop is always in O1. Right? You can guarantee O1 time if you use a linked list-like structure. Right? So in these linked structures, you should know that they are normally implemented in terms of what are called nodes. Right? They might have called them something else. Graph people often call them vertexes. Usually, though, they're nodes. So they show up. So these are all the CISC courses where these show up in. I don't know what the corresponding Cmpe courses are. I'm pretty sure the numbers are normally the same. So there's a Cmpe 365 as well, the algorithms course. OK, so in general, when you have a node, it stores two things. So in Java, you would store a reference to an element, and you would store a reference to another node. Right? In C, you would normally store, well, I don't know how you implement them. In C, you would normally store a pointer to an element and a pointer to the next node, or a pointer to one or more other nodes. Right? The generic term for this are the references to the other nodes. These are called links. Right? OK, so nodes for a stack. So a stack is just a linear collection of elements. Right? So elements are arranged in a sequence starting from the top element. Right? And each element is connected to the next element deeper in the stack. Right? So you have the top element, then the next, and then the next, and so on and so on and so forth until you get to the bottom. So in a stack, if you want to implement them using a linked set of nodes, a node in a stack would store a reference to an element, right? And then it would store a reference to the next node that's deeper in the stack. Right? So you'd have your top node would store a reference to the second node. Right? Your second node would store a reference to the third node, and so on, and so on, and so forth. So in the picture, what you would see is the following. So here's a stack that's made up of one node. Right? So we're going to keep a reference to that top node at all times. Right? Inside the node, there's a reference to a string in our case. Right? So the elements of our stacks are strings. And there's a link, which I'm showing as an arrow. So that arrow is a reference to the next node in the stack. Right? Now, this is the only node in the stack, so that reference is null in Java. Right? I guess it would be a null in C as well. Right? So you'd have a null pointer to the next node in a C-like stack. Right? OK, so if we push another element onto the stack, well, there's your element, there's your link. Right? So that's how I'm drawing them. If you push an element onto the stack, then all you do is you make a new node. Right? So you make a new node to hold the element or the reference to the next element, to the element. So there's our new node. And then you're going to set the link of that node so that it points or refers to the old top node, like that. And now you adjust our top node so that it points to the new node. Right? So make a new node. right? Link it to the next node or to the current top node, and then adjust our top node so that it points to the new node. Right? So it's just 3 steps. Oh, and then don't forget to add 1 to the size of the stack. Right? So that's, it's easy to make that mistake. So when you're removing or adding something to a collection, don't forget you have to adjust the size of the stack if you're keeping track of the size. Right? And so if you add another node to the top of the stack, right, you'd end up with that picture there. To pop an element off the stack, it's very straightforward as well. Right? So I have a reference to the top node, which means I have a reference to the element. So I'm just going to remember that the top node contains C. Right? Then I want to unlink the top node. I want to, oh, actually I'm going to set top. Okay, we'll do it that way. So I'm going to adjust top so that it I'm going to adjust top so that it points to the next node in the sequence. Right? I'm going to do this first because the way I'm going to get to this node is I'm going to follow that link right there. Right? So top points at the current top node. If I do top next, that takes me to the next node in the sequence like that. Right? And then I can remove, and that node disappears. Right? Then subtract 1 from the stack size. This node disappears in Java on its own for free. Well, not for free. The programmer doesn't have to do anything. Right? In C, you would have to deallocate that node. You'd have to free that node. In Java, though, there's no one has a reference to this node anymore. Right? As soon as you adjust that top reference, there's no reference to that node. So in Java, the garbage collector will eventually come along and remove this node. Right? So you don't actually have to specifically get rid of this node yourself. It will go away on its own like that. Right? And then, of course, don't forget to subtract 1 from the size of the stack. And of course, you're going to return the reference to the element that was just popped off the stack. OK, so what does a node look like if you were to draw it as a UML class diagram? Well, a node, right, is an aggregation of one element. Right? In this case, it's a string. Right? But a node, every node has a reference to another. A node can have a reference to another node. So it's also an association of another node. Right? So it has a link to it or a reference to its next node. Right? In a stack, there's always 1 or 0 next nodes. Right? OK, so what is our link stack class going to look like? Well, it's going to implement the stack interface. Right? Now that it's a linked stack-based implementation, we have a reference to the top node of the stack. Right? And for convenience, we're going to keep track of the size of the stack as well. Right? You don't technically have to keep track of the size because you can always compute the size by counting the number of nodes. But that's wasteful. Right? We might as well just keep track of the size. OK, now, what about our node? Right? So we need a class to represent nodes. So I'm going to make that a static nested class. Right? So notice here we've got a node. We have a class node. It's private, but it's also static. So I'll explain what a static nested class is in just a second. Right? So what's inside of a node? Well, a node has an element, right? A reference to an element, which is a string. And it has a reference to the next node in the sequence. Right? Now, a static nested class is just a class. So you can add constructors and methods to this class if you want to. Right? I'm going to add a constructor that lets you set the element and the link just by calling the constructor. Right? You don't have to. You could just leave this as elem and next and have nothing else. Right? So in other words, you can just leave this as 2 bare fields. Right? And then whoever's using, then the linked stack class will access the fields of the node directly, which we're going to do anyway. But it's convenient to have a constructor. OK, so what's a static nested class? Right, so a static nested class is the simplest kind of nested class that you can have in Java. Right? In a lecture from a couple of days ago, we had a inner class. Right? An inner class is a nested class that's not static. Right? So a static nested class is just a regular class that happens to be defined inside of another class. Right? So in other words, it behaves exactly like a regular class. unlike other kinds, so unlike inner classes, right, a static member class cannot see the fields of the class that it's defined in. Right? So in other words, node does not see the private fields of linked stack. Right? Also, unlike an inner class, right, an instance of a static member class can exist in isolation of the enclosing class. Right? So in other words, this means I can have a node. I can have a node object without a linked stack object. Right? Now remember, with an inner class, that's not true. Right? So for the inner class, you couldn't have a range iterator without a range to iterate over, right? Which is why it was an inner class. Right? I want nodes to exist in isolation of, or we need nodes to exist in isolation of a stack. And so we make this a static member class instead. Okay, so what is our constructor for linked stack do? Sets the size to 0, and it sets the reference to the top node to null to indicate that there is no top node. Right? So that makes an empty linked stack. Size is straightforward. You just return this dot size. Right? So that's a no-brainer. Okay, how does push work? Right? So remember how push works? So this is just the same slides from before. Right? If I want to push an element onto the stack, I'm going to make a new node. So that's step 1. Right? Step 2. You're going to set the link of the new node to point to the current top node. So in goes the link. We're actually going to do these in one step because our constructor will do that for us. Right? And 3, set top to refer to the new node. So we're going to adjust this dot top to refer to the new node. And then we're going to add 1 to the size of the stack. Right? So if you just follow the picture, it's very easy to implement this method. It's very easy to implement push. Right? So push takes in a string. We're going to make a new node. So we make a new node. It stores the element. And it also sets the next link to point at the current top of the stack. Right? So that node n now points at the current top of stack. Right? I want to adjust the current top of stack to now point at n. And then I increase the size of the stack by 1, and that's it. You're done. Right? So there's push. Push in 3 lines. What about pop? So for pop, I want to remember that there's a C sitting here, right? Because I need to return that C back to the caller. Right? So I'm going to obtain a reference to the element stored in the current top node. That's easy, right? I have a reference to the top node, so I can get the element just by top.elem. I want to then set top to refer to the next node deeper in the stack. Right? So the next node deeper in the stack, if that's top, that's just top.next. Right? So it's easy to adjust. It's easy to do this. It's just top equals top.next. Right? And then step 3, subtract 1 from the stack size. Right? So pop is also easy. Okay, so you can't pop an empty stack. Right? So if we try to pop an empty stack, we throw an exception. Step 1, remember what is the element that was on the top of the stack. Right? Well, that's just this .top.elem. Right? So we're just going to go into the node and grab the element from the node. Right? Make top refer to the next node in the sequence. Right? So the next node in the sequence is just this .top.next. Right? So this top equals this .top.next. Right? Decrease 1 from the size, and then return the popped element. And that's it. There's your linked stack-based implementation in about a dozen lines of code. Right? Okay, if you wanted to make this, though, if you really wanted to make this a useful Java class, then you would do things like put in equals and toString and things like that. Right? But for those types of methods, you have to iterate over the sequence of nodes. Right? I need to know what are the elements in the stack. So now we have to iterate over the nodes. Right? But if you go back to the class, right, you don't actually have a list or any sort of collection of nodes. You just have a link. You just have a reference to the top node. Right? That's all we have. So to iterate over the sequence, we somehow have to iterate over this chain of nodes. Right? And it turns out that iterating over a sequence of linked nodes in any data structure that you implement is a very common operation. Right? So whether you're implementing a stack, a queue, or a list, priority queue, right? If you're doing it with some sort of link structure, you're probably going to have to iterate over the sequence of nodes. It's not hard to do, right? Because you know where the end of the sequence is. Right? The end of the sequence is indicated by a null next link. Right? So at the end of the sequence, you run into a node that has no next link. So you just loop until you find a node that has a null next link. So start at the first node, which is just the top. Right? Simply follow each link to the next node until you find a null node. Right? And so the general iteration pattern is as follows. They should have taught you this in your C course too, right? Your data structures course. So I'm going to start at whatever your starting node happens to be. Right? As long as that node is not null, you've got something, right? You've got something in the sequence. So you do whatever you need to do with n there, right? Get its element, do something with its element, whatever, right? And then you advance to the next node. Right? So how do you make n move to the next node? Well, n just becomes n.next. Right? When you hit the bottom node in the stack, n next is going to be null. Right? So when you come back up to the top of the loop, n is null, and so the loop stops running. Right? Now, whatever you do, if you end up writing code that looks like this, you cannot use n here, right? Because n is null. So if you try to dereference it, you'll end up with a null pointer exception. In C, you would have a null pointer. Oops, what did that just do? Okay, so we're going to iterate over the sequence of nodes. So n starts at the top, right? Is n null? The answer is no, right? It actually points at a node, right? So do something with C, and then follow the next link, right? So the next link is just n.next, so it's just that thing there. So that takes us to the next node. Right? Is n null? No, it points at a node. Right? So do something with B, follow the link to the next node. Right? Is n null? The answer is no. So do something with A, and then follow the link to the next node. Right? So n is now null, so the loop ends, and you've done something with every element in the list in the stack. Right? So for example, toString, you could implement just by following the nodes in the stack. Right? I'm going to use a string builder here. I don't think I've shown you a string builder yet. String builder is the mutable version of string in Java. So if you want a string where you can actually change the characters in the string, you want to use a string builder. It's more efficient than joining strings together yourself. It's basically a list of characters. Right? So you start at the top. Right? So here's our general iteration pattern right there. Start at the top. Well, n is not null, so I have a node, right, that contains an element. Right? So I'm going to append a new line character. Then I'm going to append the element as a string. Right? And then I'm going to advance n to go to the next node. Right? So, and then at the end, I'm just going to ask for the string representation of the string builder, and that implements toString. Right? Equals would be very similar. Right? So for equals, you put in all the equal stuff up here. Right? So if obj equals this, if this get class is not equal to obj get class, et cetera, et cetera, et cetera. Right? And then you loop over the nodes and test whether or not the elements are equal. Right? As soon as you find a pair of elements that aren't equal, you return false. Right? If you visit all the nodes in the sequence, then you return true. And that's it. So nodes are an example. So a node is an example of structural recursion, right? So every node has a reference to another node, right? That node has a reference to another node, right? That node has a reference to another node, and so on, until you eventually get to a null link. Another way to look at this is that if you look at a stack that's made up of a bunch of linked nodes, if you look at any one of those nodes, right, that node is also the top node of some stack. Do I have a picture here? Hang on, just here, right? So in this picture here, right, C is the top of that entire stack. Right? B is the top of the stack with two elements in it, and that A is the top of a stack with just one element in it. Right? And so that makes thinking about recursion on stacks very easy to do. right? Because you can just treat a node as though it were the top node of a stack. Right? So I can take toString, right, this iterative version of toString, and easily convert it to a recursive version of toString. Right? So our recursive version of toString, we split it into two separate methods. Right? One of them is the actual recursive method. Right? The original toString, this one just calls the recursive method. Right? So toString starts out by making a string builder. Right? It sets n to be equal to the top node of the stack. And now it's going to call the recursive method. So the recursive method generates the string representation of a stack where that is the top node of the stack. Right? So once more, right, the recursive version generates the string representation of a stack where that is, where that is the top node of a stack. Right? So our base case, right, is if n is null. Right? So if n is null, the stack is empty. Right? So for the empty stack, I'm just going to return the empty string. If n is not null, right, I want the new line character followed by the element that's in the current node, right, followed by the string representation of the rest of the stack. Right? The rest of the stack just starts at n.next, right, because every node is the top element, can be considered to be the top element of a stack. Right? So n_next is the top element of a stack that's one smaller than n. Right? And that eventually produces the string representation of the entire stack. Right? And then you can just return the string representation of the string builder, and you're done. Right? So you can always turn these iterative algorithms into a recursive one if you wanted to. Normally, you don't do it with linear structures, linear data structures, because it's often easier to write the iterative version than it is to write the recursive version. Did you guys do binary search trees? Yeah. Okay. So you probably would have seen recursion on those, right? And it probably was much easier to do recursion on a binary search tree than it is to write the iterative version of the methods. Did they show you the iterative versions of the methods on a binary search tree? It's all recursion, right? Yeah. The iterative versions, a lot of them will use a stack. All right, so what do we got next? Oh, inheritance. Okay, so this really does move into part 3 of the course now. Well, we're towards the back half of part 3 now. All right, so inheritance in Java is a relationship between two classes. So it's the strongest relationship that you can have between two classes. Right. So inheritance in Java is the relationship that models what happens when one class is derived from another class. Right. Now the idea behind inheritance is simple, powerful, and easy to misuse, unfortunately. Okay, so when you want to make a new class, right, normally what you do is you shop around for an existing class, right? You say, well, I need something that does X. Is there some class that already does that? Right? Often what happens is you find something that sort of does that. Right? And so if there's a class that already does a lot of what you're looking for, right, then you can use inheritance to reuse that class. Right? So what you can do is you can derive your new class from the existing class. Right? And what that ends up doing is you end up being able to reuse all of the fields and methods of the existing class without having to write and debug them for yourself. Right? So so one way to think about inheritance is as a code reuse mechanism. So inheritance, if you remember the object model, right? So there was abstraction, encapsulation, modularity. Inheritance is part 4 of the model, along with interfaces. Right? So part 4 of the object model was hierarchy. Right? And so interfaces and inheritance, those are the two Java mechanisms for supporting a hierarchy of classes. Right? So inheritance in Java looks like this. This is not a UML class diagram. This is just a plain old diagram that sort of shows you what the Java class hierarchy looks like. So at the top of the hierarchy is java.lang.object. Right? And so every class in Java is derived or inherits from big O object. Right? So you can see that underneath object, there's a bunch of classes, right, that all directly inherit, that are all directly descendant from object. Right? This class here has another class underneath it. So this class inherits from that class, and that class inherits from that class. Right? This one down here inherits from here, which inherits from here, which inherits from here, which inherits from there. So a subclass, or a derived class, or an extended class, or a child class, these are all names for the same thing. I'm going to stick with subclass and superclass for the most part, right? Or occasionally child class, right? So a subclass is a class that's derived from another class. So if you were to draw this as a UML class diagram, the subclass has an arrow that points to the superclass. The arrow is an open arrow. The superclass, or base class, or parent class is the class from which a subclass is derived. Right? So big O object is the superclass. It's actually the superclass for all objects in Java, or all classes in Java. Right? So string is a direct subclass of big O object. Right? Our point2 class is also a direct subclass of big O object, right? And every other class that we've implemented so far. So you can have a class that's derived from something, and then you can derive from that class, and then you can derive from that class, and so on and so on and so on. There's no limit to how far you can go, right? Eventually, in Java, you always get to big O. You always get back to big O object, right? So you can have a class X that inherits from object. Z inherits from X. And then A inherits from Z, right? And you can so on and so on and so on and so on. A class is said to be descended from all of the classes in the inheritance chain going back to object. All that means is that A is descended from Z and X and object. Right? Z is descended from X and object, and so on and so forth. Right? The classes from which a class descends from are called the ancestor classes. Right? So A's ancestors are Z, X, and object. Oh, notice the arrow here is actually significant. Right? So the fact that A points back to Z, so not only does it indicate inheritance, it also indicates that in Java, it also indicates that the relationship here is one way. Right? So in other words, A knows something about Z. Z does not know anything about A, which is a bit odd, right? But that's the way it works. Okay, so why are we using inheritance, or why would you want to use inheritance? Right? So a subclass inherits everything that's not private from its superclass. Right? Everything except constructors, sorry. So any non-private fields and any non-private methods, the subclass inherits. Non-private includes package private, by the way. Right? So anything that's public or protected, the subclass inherits. And by inherits, I mean that the subclass has access to those things directly by name. Right? So if there's an existing class that provides some of the functionality you need, you can derive a new class from that existing class to produce a subclass. Right? Your new class has direct access to the public and protected fields and methods. Right? Direct access means you don't redeclare or redefine them. Right? So you don't, if you have access to some field, you don't produce a duplicate copy of that field in the subclass. Right? If you have a method, if you inherit a method that you want to use in its current form, you don't redefine the method. Right? So you don't have to re-implement everything. You can just reuse the existing implementation. Now, if you want to, right, your new class can add extra information and extra methods to itself. Right? So you're allowed to add new fields, you're allowed to add new methods, right, which your new class knows about. The parent class or the superclass does not know about the new fields or the new methods. Right? So again, the relationship here is primarily one way. If you want to, right, you can redefine or override the methods that you inherit from the superclass. Right? So every time we've been writing at override, or every time we've been implementing equals or toString, we're actually overriding the superclass method that came from big O object. Okay, question?
Is it not like kind of inefficient if you are then making one, but you don't use all of the methods from like the superclass?
So you have all the methods. So
Or some, but I reference all. Is that effective?
So the methods don't take up any memory, right? They only take up memory when you run them. So they don't actually take up any memory. So in terms of memory use, it's not inefficient, right? It is possible, I suppose, that you inherit from some class and you don't actually need all of the fields of that class. So in that case, you would pay the price of having stuff that you don't need. But it's unlikely to be the case, right? Because the class that you inherit from probably needed those fields. Otherwise, it wouldn't have declared them. Yeah. Okay, so remember, inheritance is a relationship between two classes. So it must model some kind of relationship. It models the is-a relationship between two classes. So is-a means is substitutable for. Right? So that's what you really should think about. That's really what you should remember when you think about inheritance. Right? So is-a means is substitutable for. Right? So string inherits from object. So what does that mean? It means a string object is substitutable for a big O object. Right? Anywhere you need a big O object, you can use a string object. Right? What it's supposed to mean in Java is that a string object is able to do everything that a big O object says it can do. Right? So your subclass is supposed to be able to do everything that the superclass says it can do. Right? Actually, it's supposed to be able to do everything that any ancestor class can do. Right? So is substitutable for, right? Remember that phrase. Right? All right, in Java, object is special. Right? So it's unique. It's the only class in Java that has no superclass. Right? And so that means it's also the class from which all other classes are descended from. When you make a class and you don't explicitly state what class you inherit from, then object becomes the class that you inherit from. Right? So point 2, its superclass is in fact big O object. Right? Your matrix class from your lab, its superclass is also big O object. All right, in Java, a superclass can have as many subclasses. There's no limit on the number of subclasses that a superclass can have. Right? What you should also remember is that the superclass has no idea what subclasses it has. Right? So there's no way for you to know from the superclass what subclasses exist. In Java, a subclass has exactly one superclass. Right? So in Java implements what's called single inheritance. Right? So this picture here, Y, its one superclass is X. Z, its one superclass is X. And W, its one superclass is X. Right? There is no relationship between Y and Z or Z and W. Right? So there's no explicit relationship here. Right? The only relationship that exists here is between the subclass and its superclass. Right? The superclass X does not know about Y, Z, or W. Right? And there's no way for it to know about Y, Z, or W. All right, last slide, I think, and then yes. Okay, last slide, and then I'm going to call it quits because I have to run back to my office. All right, so Java implements single inheritance. Some programming languages allow you to inherit from more than one class. Right? So there are languages that allow what's called multiple inheritance. The Java language designers decided to only support single inheritance because it prevents the deadly diamond of death problem. That's a real name. I didn't make that up. You can Google it. You'll find a Wikipedia page for it. Right? So this is not Java. Right? So this is some language that supports multiple inheritance. Right? So in a language that supports multiple inheritance, right, you can have a superclass X. Right? It has two subclasses Y and W. Right? And then Z is allowed to inherit from both Y and W. right? So if X has a method called f, right? Y and W both decide to change how f works, right? So they're allowed to override f, right, to change how it works. The problem that you run into in Z is which version of f does Z get? Does it get the one from Y? Does it get the one from W? Does it get the one from X? Or what exactly happens, right? So those languages have to have some mechanism that resolves that problem, right? And there is no universal solution to this problem. So every language has a different way of dealing with this problem, right? Java decided that they wouldn't deal with the problem, and so they only allow single inheritance. All right, so let's call it quits there. We'll continue this discussion in the next lecture.